Hi everyone, my name is Kostas Tsalapatas and I'm a second year PhD student working with Professor Jesper Solerman and the ZF collaboration here in Stockholm. For this ZF science vlog, I would like to talk about a paper that we recently published and which was about a thermonuclear supernova that interacted with nearby circumstellar material, or CSM in short. Now, this explosion had a lot of spectacular properties, and many of them were observed for the first time ever. So let's get to it. Now, thermonuclear explosions are the type 1A supernova, and this type has very standardizable light curves, meaning that they can be used as excellent distance indicators, and it is this type that is used in cosmology. However, while we understand that they are the explosions of white dwarfs, we still don't understand how white dwarfs explode in the first place, or what are the progenitor pathways that lead to exploding conditions in these stars. Regarding the progenitor pathways, there are two cases. In one, the white dwarf is accreting material from a living star, and in the other, two white dwarfs merge or collide to produce an explosion. So how do normal 1As compare to the 1A CSM subclass? Well, spectrally, normal 1As have these broad absorption features that are coming from the expanding ejecton. On the other hand, 1A CSM show narrow emission lines that are formed in the CSM around the explosion. When it comes to the light curves, 1A CSM are more bright than 1A, and that is because the interaction with the CSM is an additional mechanism that produces more light. And this is also why 1A CSM are slower to evolve, meaning that they remain bright for up to hundreds of days longer than 1A explosions. SN 2020 AU8, which was the focus of the paper, began with a fairly typical light curve with a bell shape, nicely behaving. And the first spectrum, the classification spectrum, was best matched to a thermonuclear class. And that was great. Okay, now we know what this object is. And when we were expecting this object to fade away, well, it didn't. Instead, it proceeded to produce a spectacular second peak, even longer duration. And this secondary brightening is first time observed for a 1A CSM, but this is hardly the most interesting thing about it. What is even more interesting about this object is the interaction spectrum. But to understand why they're so interesting, let's take a step back. Now, 1A CSM typically look like something like that. They have these narrow hydrogen lines, meaning that the CSM around the explosion is rich in hydrogen. And that was, and still is, one of the best evidence for the very existence of the single-degenerate progenitor pathway. Now, before our object, but on the same year, SN 2020 EYJ was discovered, and that was the first time where 1A CSM had numerous lines of helium. That showed that helium stars can also be companions to exploding white dwarfs. And then came 2020 AU8, which didn't show any hydrogen or helium. And this is very problematic because we don't expect the companion of a white dwarf to produce circumstellar material that is poor in hydrogen and helium. The narrow lines that we see instead are best matched to carbon and oxygen. To better understand what's going on, we modeled the second peak with an interaction model and inferred masses for the CSM between 1 or 2 solar masses. This is relatively low, but they should be treated as order of magnitude estimates because the model that we used is a semi-analytical one, meaning that it uses a lot of crude assumptions that may break down in the case of our explosion. In summary, 1A CSM as a class are thought to arise from the single-degenerate progenitor pathway. But many of the observables, if not all of them, in SN 2020 AU8 are in class with this picture. So for the first time ever, we introduced a discussion on the double-degenerate progenitor system to produce a 1A CSM. And while it has its merits, it is still difficult to reconcile with some of the observables And one of the difficulties is the fact that the physical mechanism through which as the secondary white dwarf can be stripped of its material before the explosion remains still poorly understood. With that, I would like to thank you for viewing and invite you to reach out if you have any further questions about the paper. Thank you.